Okay, good evening everyone. Welcome to the third video on the ideal gases and real gases problems. Okay, so this question is taken from the 2003 May paper, and this is a continuation of one of the problems there, okay, B2. And the first part of the problem was completely related to thermodynamics. Of course, the current syllabus of IB has thermodynamics, but I'm not dealing it over here. This is a concept problem, so this concept is entirely related only to ideal and real gases. So I'm not bringing into anything else over here. Okay, now let us continue with this. So the paper is already been posted in my WhatsApp group. If you want to know the WhatsApp group details, then you can look into my comment sections. Okay, or you can join this here. So this is my WhatsApp group. One day before, that is in the morning, today morning I post this paper, and today evening by 8 p.m. you will be able to see the solutions for these videos, for these questions. So it is https rebrand.ly/ib physics with raw. This is the URL for this. Okay, it's a shortcut URL over here. So you can just type in this in your browser and you will be getting a group. The group name is Misconceptions in Physics, which has an emblem what is being shown over here. Okay, the same logo. So you can just join the group, and every day you will be getting one question paper. You can solve this by evening, and by 8 p.m. today or maybe next day, if not possible today, okay, then definitely I will be posting the solutions also. You can look into it. Already the previous solutions what had been doing so far is already been available in my website. My website name or link is also the same, which is ibphysicswithraw.com. So this is my website name. You can refer to this also. All the past papers from 2016 to 2024 for IB curriculum has already been uploaded to it with complete solutions for paper 1. Paper 2 also, some of these questions are being uploaded, and there has been a categorization of these questions based on the concepts. So what you can do is you can learn one concept and then you can look at the questions there, and so that you will get to know about what are all the variants of that particular concept being asked in IB, and so that you can complete it. Okay, that's one strategy, one way of studying papers or start doing a revision over here. Okay, now let us move on with this question. A sample of an ideal gas is contained in a cylinder fitted with a piston as shown. Okay, so you have this. Explain in terms of molecules what is meant by the internal energy of the gas. The same question has been asked several times. Anyway, if you still want, I'll just solve this one here. So in terms of the internal energy, okay, in the previous question, in the previous video, you would have seen a similar question was asked, but it was about ideal gas. And previous to it here, in the first question, I had asked the same question over here. It says about explain in terms of microscopic kinetic model of an ideal gas, the difference between temperature and internal energy. Okay, so somewhere in every paper, most of the papers I have seen that somewhere there's a relevance, there's a question which is related to temperature and internal energy. So get to know most of it. Okay, so what is internal energy of the gas in terms of molecules? In terms of molecules, we can say it is the total energy of the molecules, which is equal to, use this word, random kinetic energy plus potential energy. Okay, so this word should be appropriately used. Okay, so only then you'll get 2 marks over here. Then the piston is moved inwards, decreasing the volume of the gas suddenly. Okay, you move it inwards suddenly by considering the speeds of the molecules. Suggest why the temperature of the gas changes. What happens to the temperature of the gas and why does it change? Okay, so what do we do? Now the piston is over here, suddenly gush it and push it across. As a result of it, the piston comes here. Okay, let us say the time taken by the piston to start from position A and to reach position B is, let us say, 0.1 second, 10 power minus 1, 1/10 of a second. Now the molecules which are present over here, okay, are very happy. Now as a result of it, the moment you push this one here, what will happen? The molecule which is slowly going over here is now hit with a bat, right? It's something like you throw a slow ball to a person, a very good batsman. What will do? He'll just hit it across. So as a result of it, the molecules will now start flying. Okay, there's a possibility that the molecule can even achieve a sixer, right? So it will immediately go faster. The moment you say it goes faster, now we will write it down because that is required. It's not a story. The piston suddenly moves. Why the temperature of the gas changes? The first one, what does it do? A moving molecule towards the piston gets hit by it and rebounds with a speed higher than its initial speed, right? So initial speed. Now the moment it hits this one and it goes at a higher speed, now it will definitely go and hit another molecule. Maybe there's one molecule, lazy molecule, which is just slowly moving here. Just it goes and hits it here, and suddenly the second molecule starts moving, right? So now what will happen? So as a result of it, more number of collisions will occur. Okay, and then thirdly, kinetic energy of all molecules will increase. Those which are lazy molecules will also now start colliding, and as a result of it, they will also be moving with some speeds, right? Okay, when they are moving like this, definitely kinetic energy will increase. In other words, you say the average kinetic energy of all the molecules increase. When average kinetic energy increases, what happens? Temperature will increase. Okay, since we mentioned the reason, since temperature is proportional to average kinetic energy. So 5 points. Okay, here 3 points, and here it is one more point. 4 points, the fourth one plus 1/5 one here. I mentioned all this, and as a result of it, you get complete 5 points over here. Okay, this is how one needs to write in an exam. Then next, the gas now expands at constant pressure P, so that the volume increases by an amount delta V. Constant pressure P, but volume increases by an amount delta V. Derive an expression for the work done by the gas. Now P is constant. Okay, and there is an increase in the volume delta V. So you want to find out what is work done. What is work done? Let us take up a piston once again. We take up a piston like this, and I had initially the piston's handle was here. Now what did you do? You applied a constant pressure. As a result of it, the piston started moving in this direction. Let us say the distance moved by the piston in a given time t is delta x. The piston is here. Now let A be the area of the piston. Okay, I'll consider it like this. Maybe some of you might consider circular. I am considering square over here. This will be the area. This will be the area of cross section. Okay. If this is the area, then you see this area multiplied by, let us say this is your first length L1. Okay, initial length L1. So area multiplied by length 1 will be equal to volume, right? Okay, let us call V1 over here. Now what we do is let us consider work done. What is work done according to you? Work done according to us is nothing but a force multiplied by distance, right? Displacement, force multiplied by displacement, which should now be, if I remove the dot product here, I can now raise this as a Fs cos theta. Okay, Fs cos theta. Now towards it, what is the force over here? P is the pressure applied over here across an unit area of cross section, because this will also have the same area of cross section here, right? It will also have the same area of cross section. So therefore, force will be written as pressure into area. So I will write once again W is equal to, I will substitute for force, pressure into area, into displacement. What is the displacement? It has moved by this displacement. Delta x is your displacement. Delta x into cos theta. What is cos theta? The direction of the force, the angle made between the direction of force and the direction of the displacement. How is the force directed? Like this. How is the displacement directed? Like this. So they are parallel vectors. When they are parallel vectors, what is the angle between them? Theta equal to 0. So therefore, this becomes cos of 0, which will now be equal to PA into delta x. Okay. Now what we'll do is, see here I have written A into L1 equal to V. Area multiplied by this full length, T equal to 0. This was the position of the piston. After certain time, the piston is here. Piston is over here. The piston is over here. Now let me consider that this distance is L2. This distance is L2. So therefore, can I now write V2? Okay. Can I now write V2? The final volume is equal to A times L2. See, which is the final volume? This volume, right? So this is your final volume, A times L2. So as a result of this, now what I can do is, I can also write, if I take delta V, okay, change in volume, which is nothing but which is higher, V1 minus V2, if I take which is equal to delta V, I can now write this as A into L1 minus L2. right? What is L1 minus L2? Look at this. This is your L1, this is your L2. So this L1 minus L2 is this delta x over here. So therefore, now I can now write here as V1 minus V2 or delta V is equal to A into L1 minus L2, which would be A into delta x, right? A into delta x. So therefore, I have already got delta V is equal to A into delta x. I will take this value, see here, I have A delta x here. I take this and substitute it over here, which should be P times delta, right? This is the work done at a constant temperature at a constant pressure is applied on the gas, which increases the volume of the object, where increases or decreases the volume of the gas. That is given by W is equal to P times delta. This is the formula that we need to derive. Okay, let us stop this here. Let us continue with the next video, the next question. Thank you.